In this video, we're going to introduce the topic of improper integrals. Here we're looking at type 1, infinite limits of integration. Consider the definite integral from 1 to t, 1 over x squared dx, for any real number t larger than 1. This definite integral gives the area of the region bounded by y equals 1 over x squared, the x-axis, x equals 1, and x equals t. So the area is represented by a of t is equal to integral from 1 to t, 1 over x squared dx. All right, so now let's evaluate a of t equals integral from 1 to t, 1 over x squared dx. The first thing we'll do is we'll write this in fractional form, makes it easier to integrate. So we'll write this as x to the minus 2 dx. Now we'll apply the reverse of the power rule, so we get x to the minus 2 plus 1, that's negative 1, minus from 1 to t. And let's rewrite this as negative 1 over x from 1 to t. Now we can apply the fundamental theorem of calculus. So we're going to get negative 1 over t minus 1 over 1. If we simplify this, we're going to get 1 minus 1 over t. So this is the area of t. So a of t, the shaded area, is 1 minus 1 over t. We like to know what happens as t increases without bound. So let's look at some values for a of t as t increases. So let's consider t equals 1. When t equals 1, we plug t equals 1 in here, and we're going to get 1 minus 1 over 1, well, that's just 0. Let's plug in t equals 2. So we get 1 minus 1 over 2, that's 1/2, so the area is a half. Let's plug in t equals 3. Plug 3 in, you get 1 minus 1 over 3, that's 2/3. So now let's look at something larger. Say put t equals 100. 1 minus, the area will be 1 minus 1 over 100, that's 1 minus 0.01, so that gives us 0.99. So it's clear as t increases up to infinity, then the area approaches 1, the area under the curve. So that's basically what we notice, the limit as t approaches infinity. So limit as t goes to infinity of a of t is equal to limit t goes to infinity of 1 minus 1 over t. Now 1 over t is going to approach 0 as t goes to infinity, so the result will be 1. So the area of the shaded region approaches 1 as t goes to infinity. Therefore, the integral 1 to infinity 1 over x squared dx is equal to limit as t goes to infinity, integral from 1 to t 1 over x squared dx is equal to 1. We say the improper integral converges and has a finite value of 1. All right, so the key concept here is even though the region of integration is infinite as t goes to infinity, the area bounded under the curve is finite and has value 1. So now let's look at another case. Here we have a of t is equal to integral from 1 to t 1 over root x dt. I'm sorry, dx. That's integral from 1 to t. Let's write it in fractional form. X to negative 1/2 dx. We'll apply the reverse of the power rule. We get x to negative 1/2 plus 1, that's 1/2. Divide by 1/2, that's the same as multiplying by 2. Evaluate it from 1 to t. That's going to give us, applying the fundamental theorem of calculus, 2 times t to the 1/2 minus 2 times 1 to the 1/2. That's equal to 2 root t minus 2. So notice how as t increases, the area given by a of t equals to 2 root t minus 2 also increases. But in this case, the limit as t goes to infinity of a of t is equal to limit as t goes to infinity of 2 root t minus 2 will be 2 root infinity minus 2. Well, root of infinity is just infinity. So we get 2 times infinity minus 2, which will be just infinity. So the shaded region under y equals 1 over root x has infinite area. This is a key concept. Therefore, the integral from 1 to infinity, 1 over root x dx, that's equal to limit as t goes to infinity, 1 to t, 1 over root x dx, is equal to infinity. So why is it that one of the integrals converged and had a value of 1, and the other integral diverged and have a value of infinity? So let's explore that further. So notice from the graphs below, y equals 1 over x squared and y is equal to 1 over root x. They both approach 0. The y value approaches 0 as x goes to infinity. But the values of y equals 1 over root x, they don't decrease fast enough. This is the key part. They don't decrease fast enough for the improper integral to have a finite value. And for this reason, the integral from 1 to infinity, 1 over root x dx, approaches infinity. It diverges. So take a look at both of these side by side. We've got y equals 1 over root x, and we show that the improper integral diverged to infinity, and the reason was that the y value was not approaching the x-axis fast enough. Whereas on the left-hand side, we have y equals 1 over x squared, and the integral from 1 to infinity, 1 over x squared dx, this integral came out to have a finite value. It has a value of 1. It has finite area because it approached the x-axis very fast. All right. Thank you.